Welcome everyone. Thank you for joining us today. We're gonna talk about LANCP and more specifically about the line driver tracing. So for today's speakers, my name is Majd, and Stephen will be presenting for you the line driver tracing. We also wanted to mention the Dick name, and Debbie's name, Dick name, because he's the man behind the LANCP. So, and for today's agenda, we will go through first what is the line driver tracing is, and go through some user scenarios, TCP dump versus the line driver packet tracing, and also how the driver tracing works actually. Also, we're going to go through some LANCP commands and some trace setting, how you're going to set it up, and different, like how you can start the trace, stop the trace. Also, like you can do some different configurations. Then we will do some live demo, and also we're going to wrap up the day with the best practices and tips, and also what is the future for the LANCP.
So yeah, we've also included like a link to a supplementary document that Dirk worked on. So it's a more detailed explanation of what is LANCP, how to use it, or at least the diagnostic side of LANCP. Okay.
So LANCP, which is the LAN control program, is a utility built into the OpenVMS environment. It has a specific feature, which is the LAN driver tracing. Today, we're going to only talk about the LAN driver tracing, which allows you to capture and check details event on the LAN driver level. It's similar to the system dump analyzer, but instead of the system level tracing, it will operate more into the on the device level. So I'm gonna go first shortly describe how it works. Then we're gonna go more into details in the next slides. So when the system boots, the system creates a buffer where it logs all the trace entries. This buffer has a specific size between 512 bytes up to 1 million. Sorry. So once the buffer is full, the data that has been recorded in the trace buffer get discarded. First in, first discarded. And we have also 64 types of different events. 32 of them are more commonly across all the line drivers, and 32 are more device specific. Each of these entries are 32 bytes. However, when a packet is more than 32 bytes, this will be stored in different entries. Like if a packet like is 64 bytes, this will be stored in 2 different entries. Each one is 32. So we have 2 different user scenarios here. The most common, the customer we have in the customer environments, which is the most common use case, which allows you to capture and analyze the network traffic, connection problems, debug issues, and so on. While tools like TCP dump are actually commonly used for TCP/IP level traffic or tracing, LAN driver goes more deep into, and it operates directly on the device level. So depending on the issue the system manager has, they could choose between the TCP dump or the LAN driver tracing. Sorry. The second user scenario is for driver developers and engineers qualifying new devices. It's very the LAN driver tracing actually give us very more better visibility for how the system works, and if we have like any errors, or we want to debug issues, or even performance problems, or for evaluating performance. And it's also very useful in the beginning, in the phase of the developing the drivers. Or if you want to also do a comparisons between the different versions of the driver or even different configurations. So we have the TCP dump file, which allows us to calculate TCP/IP traffic that makes it to the active the TCP active interface. It's also highly flexible for it's like by filtering. You can filter by host, port, or protocol. Also, you are allowed to upload a data file as an input or do a live traffic. It's the same as the LAN driver tracing. Also, you're able to save this data into a file for later inspection if you want to do it on the Wireshark and so on. So now it's important to note that the TCP dump file is, or the TCP dump only sees traffic that makes it to the TCP IP stack. It won't capture the device level, or it won't even capture the DICnet cluster or device level packets. So of course, it's great for traditional IP-based troubleshooting. But for OpenVMS environments, the LAN driver tracing would be better because since the connection wouldn't be always by TCP/IP. Also, you have the LAN driver packet tracing allows us to calculate traffic sent and received from the device. Also does some specific analysis. Also traces at the line rate. You're able also to limit your size of the buffer. As I mentioned before, it's like between 512 bytes or up to 1 million. You're also able to run the trace in a promiscuous mode, which means normally the network processes on the network card that makes it to the network. But with a promiscuous mode, it can communicate with the network in general. So how the driver tracing works, when the system boots, the trace immediately starts. The system creates a trace buffer where it logs all the trace entries. Of course, in the memory. This buffer saves the record of the event, like packets being sent or received, depending on. You can control what gets recorded by using two different settings or filters. It's called trace mask and stop mask. When an event happens and the trace mask matches the event, that means the trace will, the trace is already running by booting the system, but the record will start when the trace mask matches the event. Also, the same thing with the stop mask. When the stop mask matches the event, the tracing will actually stop. And because the trace buffer can fill up very quickly, there are two ways to manage it. First, you can use the stop mask to stop tracing, or also you can set up a system flag, which allows you to stop tracing after a certain kind of error or a certain kind of error or performance issues. Yeah.
All right. So yeah, from this section onwards, we'll be covering some of the diagnostic commands for that the LANCP has. So specifically, the LAN driver tracing part of LANCP. So before we actually begin tracing, we have to know the traceable events that we can trace or that LANCP is capable of recording. So to do that, we use the command LANCP show dev trace header followed by the device name. Now here we will have this this output. So you can see in this output that we have the trace mask, the stop mask, and the buffer size above. Then below, just below that, is the all the traceable events. So the first 32 bits or the first 32 entries is common to is basically a common function, a common traceable event, and the next 32, starting from 32 up till 46, is device specific. So you'd also notice that there's a marked M on some of the traceable events. That is an indicator that it's toggled in the trace mask. Then if it's toggled for the stop mask, it would have an S. Then just below the traceable events, you would see the keywords that you can use to basically like a shortcut to activate the specific traceable events that you want to see in your well, when you're tracing. So for example, when you use like mall, mnon, sall, snon. So if you do an mall, it'll toggle every traceable event. Then if you do an mnon, then it's basically the opposite. Now for sall, you add all the traceable events to the stop mask, and vice versa for snon. Then you have some other keywords as well, like rtint, rtf, fint. So it's basically just a combination of some other trace masks. So for rtint, you could say it's interrupt, rdone, xissue, and xdone would be toggled. Now, I would actually go through some of these traceable events. So for example, the 1 second timer. So this is a timer maintained by the LAN driver, which periodically checks link state, LAN flag, system parameter changes, and it checks for timeout of transmit requests. So with this flag, there would be a trace entry when the timer routine begins. Now for the next one, we have interrupt. So this is essentially a trace entry is recorded when the interrupt service routine is called. Next, we have the fork processes. So the fstart, fdone, ferror, and fsoft. So these are trace entry. These trace entries record entry to and exit from the driver fork process routine, which does transmit and receive processing and error handling. If the fork was scheduled because of an error, it is either transmit timeout error, forced reset due to LAN failover operation, or debug or a debug command. Lastly, the soft error means the device was working, then the driver just decided to reset the device. And lastly, the other type of error indicates a reset will be done to recover and recover and apparent hardware issues such as timeout, transmit timeout. So any of the events that occurs, if any of the events occurs, then it will be recorded to the trace. Any fork event, fork process event. Next one, we have the state changes. So it's the first user start, user change, and last user stop. So this is essentially when this is related to the driver state, whenever it's initialized, or if it's operational but the link is down, or vice versa, it's operational but the link is up. Next, we have the R issue, well, the receive events. So we have receive issued, receive done, receive error. Just 3 of those. So it's pretty self-explanatory. So when a so when it's a receive issue, it's when a receive buffer is given to the device. And for the receive done is if a receive was completed using one of the receive buffers. And lastly is the receive error. So if you've encountered any errors during receiving the packet, or receiving the chat packet, then it would be recorded. Okay, so the next one is the size of the packets, the received packets that you're listening to. So you have like R small, R medium, R large, R full. I actually forgot the exact sizing of each of the packets, but I would be happy to well, let you guys know if you guys are interested on the exact size. Okay. Then for the X issue, XQ, X done. So this is basically the same as the receive side, but on the transmit. Then same with the transmit packets. So the transmit, the size of the packets is basically the size of the packets that it allows to be captured.
So if you're using jumbo frames, for example, that would be recorded there.
Yes. If you're going to use jumbo frames, I would recommend using the all size or the large, because if you use like a medium size receive packet or small size, then it would be broken into separate trace entries. So you wouldn't want that because it's going to be harder to read. Okay, so yeah, we could proceed to actually setting the trace settings. So you have two options to set the tracing. You have the active trace setting and the persistent trace setting. So the persistent trace setting would be saved into your permanent device database. For the active trace, it's only going to be active until you reset the until you reboot or you reset the service. Sorry, the driver, the LAN device. Now, of course, before you change the setting, you gotta list the device that you have available, so you know what device to configure. So you could use the LANCP list dev trace to get a list of all the existing devices and its active mask. Now, if you want a more detailed breakdown, you could use the show conf user. Thanks for that, Sully. So it gives you the list of the device, the version, the buffer size, even the MAC address, which the list trace doesn't give you. So the list trace would only give you the trace mask and the stop mask, as well as the buffer size. So only LANCP related for that one. Now, okay, so if I'm going to set like active, I just want to set for the current session, the active trace setting, I would use this command. So it's just LANCP set dev trace equals the parentheses, then the mask, your trace mask, the buffer size, the stop mask, or any keywords that you want to use. So the keywords, we can go back to this. The key, some of the keywords that are available is found here, but you can get a more complete list using the QR code earlier. So the document has a full list of the supported keywords, or just use help in then for the mask, well, I would just show how you set it up later, the exact value that you have to input. But yeah, let's proceed with just this for the moment. The next is next is the persistence. So if you want to save the settings, the trace settings in your permanent device database, you just input LANCP define. So just shorthanded it, and the rest is the same syntax as the set, as the active trace setting. Next is the clear active trace. So this just clears the existing or active trace setting that you have. So it's paired with the first command we have here. Now, if you do a clear or a purge, it would also clear your buffer. So any trace entry that you have would be completely erased. So be careful using the command if you're actively, tracing something. So clear active trace, it just clears your active trace setting. Then clear the purge command
would clear the setting on the permanent database. Okay, so yeah, managing trace data. So this is just the basic commands of starting it, pausing it, stopping it, extracting it, viewing it, or even viewing viewing a dump file from viewing a file generated by LANCP. So for start tracing, it's basically the setting. When you set up a setting for LANCP, it automatically starts tracing, begins tracing. It begins listening to the whatever events you have enabled in the trace mask. Then for pause tracing, this would temporarily halt the tracing. So it won't delete the buffer. So this is what you want if you want to, just view the current captured trace events. Next is the stop tracing. So this is sort of, this is sort of equivalent to the one we have here, the clear. So it does a similar effect. So for this one, I think it retains these trace mask setting, the stop mask setting, but it stops the tracing and it also deletes the what you have in the buffer. Next is we have the extract. If you want to extract it to a txt file or a dump file or a pcap file, you could use this command. So just append the show dev trace dev name with the what do you call this? The flags. So if you want to use it locally, you could just use trace the txt or the dump file. Now, if you want to use a Wireshark, you could just add the pcap at the end. Next is if you just want to view the captured trace events, you could just type in show dev trace. See if you already have a dump file or a file containing like a trace event, you could also do a show dev trace, the device name, then the input and the file. Okay, so before we go into the demo, I would like to point out some differences between the Alpha Itanium 64 Itanium versus the x86. So for one, there's only a single trace mask for receive and transmit. So it is because of that, because of that, we don't have a flag for specifying the size of the packet that we want to capture. So what happened was we had to define that through the buffer size. So for example, if I have like a buffer size of 512, with this formula, so buffer size plus 0 to 3. So if I have a buffer size of 512, I would be capturing small packets. Now, if I have a buffer of 513, 512 plus 1, I would get medium packets, capturing medium packets. 514, I would start getting large packets. Then 515, as a buffer size, I would start getting full packets. Then for the command, we have a limitation for Alpha and IS64. So we can't see the traceable events using show dev trace header. So the / header is not available in the Alpha and IS64, but it is included using this command. So when you do a show dev trace in x86, it would show you all the trace entries, but in Alpha and IS64, it would show the traceable events first, the one we saw earlier, then the actual trace entries. And we also have another limitation, which is the keywords. It's not available yet, so we don't have any shortcuts for that. Tracing packet. And for the tracing packet data condition, I believe you have to have both receive and transmit enabled, listening to receive and transmit enabled before it is captured. So it's like a pair, receive and transmit. And in x86, I could just focus on events like receiving or transmitting. I could have one of them enabled, but in Alpha and IE64, it has to be enabled at the same time. Next is we don't have a flag, PCAP flag file. Sorry, we don't have a PCAP flag qualifier. Instead, we have you could set the file extension in this /output as PCAP.pcap. Then you're gonna get a PCAP file. Okay, so for the demo, I'll be showing you some basic commands and how to start tracing. I'll be grabbing the screen, I guess.
That cool.
Hmm?
You're in the call?
Yes, I am. Share screen. Wait. So. That's good enough.
Yeah.
Okay. So for this one, we're going to be providing a demo of how to set up your LANCP. So first of all, I want to see my existing my available devices. So I could use the showconf user. Then this would give me the list of all the devices I can configure. So EIA 0 and EIB 0. Or I could also use a list trace. A list trace would show me the device and the current trace mask and stop mask and buffer size setup. Now, we're going to be focusing on the first device. So I will do a show dev trace on the show dev trace header on the first device. Would give me the list of all the possible traceable events. So you would notice that I have some traceable events already active here, but it's not shown in the in the list trace. That's because the list trace would provide you the current setting in the permanent device database. So if I had used define instead of set, it would appear here. Now for setting up setting some trace settings, you have to put in the command set dev trace. Then you have an option to put in the mask, specific mask. So it always comes in pairs. So the first half and the second half. So you have to define here. So this is one way to set the. This is one way to set the trace mask. Okay, so for the first half, that represents the trace setting that is common to all devices. Then the second half of the mask represents the device-specific trace setting. So, for example, I want to enable, let's say, the first 4: the timer, interrupt, fork start, and fork done. So what I have to do is I have to add all of the first bit. So 1, 2, 4, and 8. So 7 plus 8, that would give me, I think, F. 15 is 8. Yeah. Okay. So I would get an F here. So I would, if I'm gonna activate or I'm gonna toggle the flags that are in the same bit, then I would have to add them together to activate them. So let's just focus on just the mask for now. Okay. Then specify the device. Let's show that trace. As you can see, I have them enabled here. Now, if I want to do stop mask as well, I could just do the same thing and back. Kidding. Okay. Then let's say I want to toggle. Let's say let's focus on the driver specific side now. So I want to disable. I want to have link state as a stop event. So I'm just gonna add it in the second half of the stop mask. And I made a mistake here.
Missing comma.
Comma, yeah. So comma for this one. Okay, there we go. Then, as you can see, as I stated earlier, you would see it's a nest this time, so it's included in the stop mask. Now, you might think to yourself that it's too much work to type in each bit. So another option is just to use keywords. So for keywords, you could totally get rid of the mask, then just type in the keywords that you want to enable. So for example, PK, that would give me R full and X full. So I would start tracing like all transmit packets and all receive packets. So EI is 0, then do a show that trace. Then I would have those enabled. But since I didn't change anything on the stop mask, it would still remain active. But all the other settings that I had for the trace mask is completely removed. A third option is instead of keywords, you could actually toggle the specific bit. So I could toggle using like M4. Then I would toggle the fork error event. Mask. Um, so check again. I had it earlier.
04.
Ah, 04. That's why.
Missed it by 1.
Okay, so I was missing the specific. So it's important to have it complete. So M04, as you can see, it's active. Okay. So let's start a sample by tracing by doing an actual trace and seeing trace entries themselves. So I'm just going to return K EI 0. Then let's do a ping. What's your device again? Time that thing.
Nothing but 237.
207. Okay, it's gonna fail. Gotta get out. Okay. 237. Sure. Okay. let's do a short ping. I should be getting
Did you extract the file on the PCAP file?
no, not yet.
Okay.
It's just started tracing.
Okay.
Okay, and show that trace. Oops. So I'm going to be pausing the trace, so I would be sure to capture only the packets from the ping. Set that trace. Okay, that's fine. That trace. Pause. Then show the trace again. Okay. I'm just going to quickly go through the output. So I don't think we have enough time for breaking down each one. Well, the actual content of the hex dump. So the first thing that we have here is this part is the first one. The first column is the trace entry number. The second column is the second since boot. The third column is the delta of the time delta of this entry versus the previous entry. So for this one, let's use 158. So you can see that there's a 137 microsecond difference between this entry and the previous one. The next one is we have the actual clock time, followed by the entry type, then the entry data on the right. Now, RCV stands for the number of received buffers. R index stands for the receive ring index. P length is the packet length. PTY is the protocol type, which is here on the lower part. Then we also have the destination address and the source address. So I think what we're seeing here is an ARP. Yeah. So what else? I think that's about it for tracing. Oh yeah, sorry. One more thing. We could also export it if we want to. So if we want to export it to a PCAP file like discussed earlier, we could just do a show dev trace, then PCAP trace sample dot PCAP and device. Okay. From this point, I could use FTP to grab it and open it in Wireshark. See here? No. I'm just gonna share the whole screen. What did I?
Trace sample.
Okay, trace sample. Like a refresh.
Yeah, it's correct. It's, oh, this is next file zero.
That's not. Yeah. Trace. Let's just use the older file that I had. Okay. Okay. So I could open this in Wireshark, then I could do my analysis here. Okay. So as suspected earlier, most of the packets that was captured was the ARP command. Yes, I know. Don't have the ping here. Yeah, if captured correctly, it would supposed to show the ping, like the destination address, source address. But this is the old file. I couldn't find a new one. Okay. Okay. let's go back to the presentation. Just some closing remarks on the best practices and plans for the future for LANCP. Is this sure? No, gotta. Okay, so next is we have, or next that we have is the impact on the system performance. So this tracing everything has a in worst case has a minimal impact of 0.55 microseconds per input output. So it's very negligible to have running even with every trace mask enabled. Next is the default tracing. So if you have the default tracing enabled, so it has like a specific flags for the default. You would see it in the previous slide. So this is the default trace setting. So whatever you have enabled here, that's default. So even with having default tracing, there's no measurable impact. Although it has a slight overhead, it has an additional 16 kV pool allocated for each LAN device. And if you really think that the LANCP would affect your system, you could just turn it off if you think performance is really critical. Next is the best practices. So one is you can enable only the necessary events that you want to observe, so you avoid any additional overheads. Next is second thing is you could just capture you could start capturing trace events during just the critical periods, the period that you want you're actually observing stuff. Then you can just stop it afterwards. The third one is what I did earlier. So if I have trace running, I want to observe the captured trace events, I would use pause. Then if you want like a deep packet inspection, you could use Wireshark. And lastly, if you want to minimize the performance impact, you could set it to default setting because it has a minimal impact. Yeah, so what today? Oh, don't have it here. I have it here. So what's in store for the future? Well, the developer of LANCP wanted, Dick wanted to implement the same features available in x86 to the Alpha and IA64 platforms. So this means he wants to include the keywords feature, the PCAP file, yeah, the PCAP. Oh, sorry, let's go back here. Okay, so the first limitation is what we have earlier was we had to separate. We had to use the buffer size to determine the packet size, the packet that we want to capture. And in x86, that's not a thing. So that's one of the things that Dick wanted to include in the Alpha and IA64 version. So also this one, the show trace header, show dev trace. He wanted to add the show dev trace header, and he wanted to include the keywords to be available as well. And the tracing pattern conditions, he wanted to eliminate the condition that you have to have both transmit and receive active, just like in x86. So whatever you have in x86, he wants to bring it to Alpha and IA64. Next is some basic quality of life improvements. So you would notice earlier in the trace, you can't see any header file defining what each column means, like whatever the number means there. Like it was seconds, it was trace entry. I had to point it out what it means before, you know, we know. So, yeah, I think that's about it. Any questions for Dick? Questions for Dick? He's in the call. Yeah, please go ahead.
Can you, if you pass the trace, can you change the mask and then continue, or do you have to stop the trace and change the mask?
Sorry, if you.
If you have a trace mask, then you trace and pause the mask, the trace. Can you change the mask and then continue?
Continue the trace.
Yes, but it would overwrite the existing trace entries.
You have to export the old.
Yes,
Yeah.
I would suggest you export the old trace record before trace entry record before you start a new one.
That guy has a question.
Favorite. Jim. All right. So if nothing else, I think thank you for coming.
Thank you.